Hey, welcome back. Today we're going to take the derivative of an exponential function, e to the x. Now, our rule for today, this is our rule, that the derivative of e to the x is e to the x. Now, we're not going to prove this in this video. I do prove this in another video. Please go ahead and click that link, and you will find a proof for the derivative of e to the x. But before we do go any further, let's talk about what the book says. Now the book is going to give it as e to the u, the derivative of e to the u, du dx. What they're really saying is that there is a chain rule here, and that the exponent is our inside function. In other words, they are saying u is a function of x. So when we take the derivative of e to the u, we would get e to the u times the derivative of u, which is f prime of x. Now, that may not make much sense, but let's take a look at an example and we will see this. Here we're given y is equal to 3x squared. We want to find the derivative. Well, to get our derivative, our rule says it's just e to the x. It's just e to whatever it says. So we're going to get e to the 3x squared. But I'm going to multiply that by the derivative of my inside. Well, there's my inside function, my power. And this is our chain rule part. So we multiply this by the derivative of 3x squared, which of course is 6x. And if you want to rewrite this, you can write this as 6x times e to the 3x squared. And there is our derivative. Very easy to do. All right. For a question like part B, for B, where we say y is equal to sine squared of e to the x. Now, one thing to remember, we don't like squares like this. They're not very functional for us. So I'm always going to rewrite this sine e to the x squared. And now when I take my derivative, dy dx, I'm thinking chain rule. I have my outside derivative. So that's going to become 2 times sine e to the x to the first times the derivative of my inside, my first inside, well, the derivative of sine is cosine e to the x. And there's one more. I take the derivative of this inside, this derivative e to the x as well. And remember, my derivative of e to the x is just e to the x. It's its own derivative. And you can leave it like this. That's fine. But the book will probably have something like this. Remember, this is 2 sine x cosine x, or that is just the sine of 2 e to the x times e to the x. You can use your double angle to simplify that. All right, let's take a look at C. All right, so C is dealing with the natural log. Now, you might remember that the derivative of natural log of x is just 1 over x. So there are 2 ways we can solve this one. One, I can just take my derivative, dy dx. It's going to become 1 over e to the x cubed. And then we're going to multiply that by the derivative of the inside. Well, the derivative of e to the x cubed is e to the x cubed times, and I have another inside, this x cubed itself, which is the 3x squared. And if you're really good, you notice that these are just going to cancel, and what we're left with is just 3x squared. Now, I know what you are all thinking. Man, Mr. Wernow, why didn't you just use the properties? Because I was saving the best for last. I could write it this way, the natural log of e to the x cubed. Use your properties. This is just saying this is x cubed times the natural log of e. Now, I could use product rule here. However, we should remember the natural log of e is just 1. That cancels. So we're really just left with the function y equals x cubed. Therefore, the derivative 3x squared. The 13th commandment, know thy properties. Okay? Know thy properties. Right after the 12th commandment, know thy trigs. All right, for part D, again, I am going to use my property. I know, because it's natural log, anytime I see natural log, I'm going to use my property. This is the natural log of a over b, which is the natural log of a minus the natural log of b. So when I find my derivative, I'm going to write out my function, sorry, my derivative, my function. This becomes the natural log of 3 plus e to the x minus the natural log of 3 minus e to the x. And now when we take our derivative, it's a lot easier. We do have a chain rule. My outside function is this natural log, and that's just 1 over 3 plus e to the x times the derivative of our inside. Well, that's just 0 plus, and our new rule, the derivative of e to the x is just e to the x minus, again, natural log of 3 minus e to the x, that's a chain rule. My outside becomes 1 over 3 minus e to the x times the derivative of our inside, be very careful, it's 0 minus e to the x, so we get a negative e to the x. And just leave it alone right there. And there's our derivative. All right, so let's see here. For part E, we're mathematicians, we like to part E. When we're taking the derivative, oh no, with respect to x, we have x squared times e to the negative x. Obviously, this is a product rule. So when we take the derivative, we will get the first x squared times the derivative of e to the negative x, which is just, remember, e to the negative x. Be careful, there is a chain rule right here. The derivative of negative x is negative 1, don't forget that. Plus the second, e to the negative x times the derivative of the first, which is dos equis, 2x. Stay nerdy, my friends. Now this is our derivative. And you might have always heard me say, you can't have negative exponents. In some cases, it's okay. In exponentials, it's typically okay to have a negative exponent. For example, like in scientific notation, where we'd have like 3 times 10 to the negative 3. That's a weird looking 10. It's okay sometimes in dealing with exponentials to have negative exponents. And that's what we have here. But if you don't like it, you can, since they both have an e to the negative x, I can put them both on bottom. And you would get negative x squared plus 2x all over e to the x. They have a common denominator then. And if this is what I would use for critical numbers right there. All right. So let's do some implicit differentiation with this. Use implicit differentiation to find dy dx. So we have e to the xy plus x squared minus y squared. So when we take our derivative, here is our e rule. So this becomes e, the derivative of e to the xy. Remember, my derivative of e to anything is just e to anything, e to the xy. But I do have a chain rule right here, and it's product. So the derivative of my inside is going to be the first, which is x, times the derivative of y, dy dx, plus the second y times the derivative of x, which is 1, plus this becomes 2x minus, remember implicit, this becomes 2y dy dx, and then that becomes, of course, 0. Simplifying, I'm going to distribute. We get e to the xy times x dy dx plus e to the xy times y plus 2x minus 2y dy dx equal to 0. And from here, remember, anything with a dy dx stays. Next year in multi, we're going to look at a much faster way to do this, by the way. So therefore, my derivative, dy dx, would equal, anything without a dy dx goes with the first, negative y e to the xy minus 2x divided by x e to the xy minus 2y. And there's our derivative. All right, go to video number 2, and we'll take a look at a few more examples. I'll see you then. Bye-bye.